Let's go through a few concepts related to momentum. So go ahead and read through this. So the correct answer here is, B. This is what we would consider an explosion. Now, it's not our everyday usage of the word explosion. We think of things blowing up. But the archer is holding the bow, the arrow is with the bow. So if we say our system is the archer that also has the bow, and then the arrow as our system, the whole reason the arrow leaves and travels is because the archer releases the bow. The force is internal to the system. And so we can say that the momentum of the system is conserved. Now, you might be able to jump quickly to that conclusion, which is great. But I want to go ahead and be consistent about the approach. We know the archer, so if we say the archer is object 1 and the arrow is object 2, we know both of them are stationary originally. There is no momentum in the system to begin with. So that means the momentum totally has to be there finally. And so the archer is 50 kilograms. We're looking for the archer's velocity. Oops, let's put in the mass. The mass of the arrow we need in kilograms, so 0.1. The velocity or speed, 100 meters per second. When we solve for V1 final, we get negative 0.2. The units, meters per second, because the kilograms cancel. The negative sign simply means that the archer travels in the opposite direction from the arrow. And that's why we call this the recoil speed. If you've ever shot a gun, a rifle, there's a recoil, you get a kickback because of the momentum of the bullet leaving the gun. You feel the pushback on the gun itself. So the speed is all they were asking for, and thus we get the 0.2 meters per second. And it's because the momentum is conserved. The forces acting are within the system itself. Let's look at another question. What do you think about this question? The correct answer is B. So when they stick to each other, just as a reminder, this is called perfectly or totally inelastic. Momentum is conserved because the reason the 2 kilogram box moves is because it's getting pushed by the 1 kilogram box. So if we account for the momentum of box 1 right immediately before the collision happens, and the momentum of box 2 at the same moment before the collision happens, that has to still be momentum within the system. Because they stick together, they have the same final velocity. So we can just combine their masses and calculate that final velocity. We know that box 2 is not moving initially, so we have the 1 kilogram times the 3 meters per second. This system has 3 kilogram meters per second of momentum, and it still has to have 3 at the end. So the two masses together are 3 kilograms, which leaves us with a final velocity of 1 meter per second. So picking up more mass, the system will move slower. So our system here, I didn't define that explicitly, was box 1 and box 2. Interestingly enough, though, if box 2 was the one originally moving, oh, not at 1, sorry, at that 3 meters per second, and it runs into and sticks to box 1, the final velocity will be different. And that's because initially we have 6 kilograms meters per second of momentum. That 2 kilograms times the 3 meters per second gives us a total momentum of 6 initially. And it still has to be momentum finally. When they stick together, that V final will be 2 meters per second. And that's all because of that initial momentum. This original question, there's only 3 kilogram meters per second of momentum, whereas if the 2 kilogram box was the one moving, it would have been 6 total. And so that would result in a greater final speed. Let's look at another question. What do you think the answer is? Correct answer here is C. So this is a collision. The whole reason either box has a change in velocity is because of the force due to the other box. And so momentum is conserved. So box 1, its momentum, plus box 2's momentum. Again, the problem says they stick together, so that means we can consider them as one mass with some final velocity. Well, box 1 has a mass of 1 kilogram. It's traveling at 4 meters per second to the right. Box 2 has a mass of 2 kilograms, but it is moving at 2 meters per second to the left. So remember, momentum is a vector. Total mass is 3, V final. Well, V final has to be 0 because this initial momentum adds up to be 0. So it's kind of a little interesting to try to think and picture 0 momentum when things are moving, but it's because of the vector nature. So V final is 0. What if the 1 kilogram box was the one traveling at 2 meters per second, and the 2 kilogram box was traveling at 4 meters per second? And again, they stick together. So momentum still needs to be conserved. This original setup would still be valid symbolically. But this time, when we put in the 1 kilogram times the 2 meters per second, oh, I didn't draw the 4 up here, sorry, plus the 2 kilograms, here, let me write the unit so we can see specifically what I'm putting in. So the 1 kilogram box is moving to the right at 2 meters per second. The 2 kilogram box, if it was moving to the left at 4 meters per second, we would put in that negative sign. The total mass would be 3 kilograms, and we would have a V final. So now this adds up. We've got 2 and minus 8 has to equal 3 V final. So negative 6, 3 V final. V final would be negative 2 meters per second, meaning when the boxes stuck together, this system would continue moving to the left because again, vectors, we're using negative sign towards the left, the system would continue to travel to the left at 2 meters per second, simply because the 2 kilogram box has a larger momentum than the 1 kilogram box. So momentum, the equation itself is nice and fairly simple in terms of relating the momentum of our objects before and after the collisions, which is nice. We don't have to worry about those impulsive forces that are not constant. Let's look at another question. Read through that. So we have a small explosion. We won't worry about the logistics of that. Our system is these 2 boxes again. Explosion, there's something in between them that pushes them apart. So we can consider that as a force internal to the system. To the system. And so momentum needs to be conserved. They move off in their individual directions. Now, they were sitting at rest on the frictionless surface, so initially this system had no momentum. Excuse me. We know the 1 kilogram box ends up moving to the left at 4 meters per second. So we need that negative sign to represent to the left. And we're trying to find out how fast the 2 kilogram box ends up moving to the right. So this final momentum, the momentum of box 1 plus the momentum of box 2, has to add up to be 0. This is similar to that archer shooting an arrow. So the momentum of -4 that the first box has leaves us with knowing the other box has to be traveling to the right at 2 meters per second. And we get positive answer. That positive answer means to the right. All right, one last question. What do you think about this? Correct answer is E. Now, in the first case, I'm assuming the brick wall is not going to crumble to the ground. We would not be able to use conservation of momentum to talk about situation 1. We can totally understand, hopefully, that the car, this is getting at the definition of totally inelastic, meaning the objects stick together. So if the car runs into the brick wall and stays stuck to the brick wall, then the car's going to be at rest. We would not use conservation of linear momentum to calculate anything in situation 1, simply because there are external forces to the system. The foundation that's holding that wall up is an external force. But in terms of understanding the definition of totally inelastic, if the car gets stuck to the wall, then it has to stop. In situation 2, the car on the left has a momentum of mv to the right. The car on the right has a momentum of 2m, but its velocity is half v to the left. So the overall momentum before the collision occurs is 0. Because these cars stick together, again, the definition of totally inelastic is the objects stick together after the collision. then option 2 or situation 2, the car on the left will stop. And similarly, situation 3, car on the left is mv, car on the right has half the mass, but twice the velocity. We need the negative sign because that velocity is to the left. And so this still adds up to be 0. Because they stick together, then they have to stop. And so all 3 situations will stop the car.